Hello. Yesterday, what we worked on led me to ask myself this question. So, are all determinants of tensors relative to tensors? Because yesterday, we showed by example that the determinant of the metric tensor is a relative tensor. So, what about any arbitrary covariant tensor of rank 2? Because that's what a metric tensor is. Is this true for all tensors of this format? So here's the way that tensor would transpose, right? You got two Jacobians, the free index is in the right place, everything else are summation indexes. All right, we take the determinant of both sides. We learned yesterday that the determinant of a product is equal to the product of the determinants. All right, so let's do an actual something with numbers, because yesterday I said it's obvious that that is equal to that. It's actually not obvious, and I hate it when people used to do that to me. And now I'm doing it. So let's do an example. All right, so let's do this one first. I prime I. All right, so in this case, now this is I and J, and this is I prime and J prime. So you just follow the rules, right? So by convention, the ones on the top, twos on the top, ones down, twos down, you get this. Determinant, this times this minus that times that. Bing. Now we do it with J's. Now, so this was J prime J, the first one, so it'd be 2, 2, and you see it goes twos across the top, 1, twos down, ones down. Okay? Determinant of that is this. Let's put them together. Since the order of multiplication doesn't matter, this is the same as that, that's the same as that, this is the same as that, and that's the same as that. So it's true. They are the same, right? So we just wind up with determinant of this tensor is equal to j squared times determinant of that tensor, because each one of these is equal to j, yes? So the determinant of a covariant rank 2 tensor is a relative tensor of weight 2. Now, what about the inverse of that? Well, I think this is obvious. That the inverse of this would be determinant of the contravariant rank 2, the tensor, would have a weight of -2, right? Okay, so there's just one combo left. What about a mixed tensor of rank 2? Uh-oh. All right, here we go. So we've got a contravariant I, a covariant J. We put our indexes in the right place. We fill in with summation indexes, and we take the determinant of both sides. All right, so let's do another example. This time, let's do a real example. If you do this with numbers or letters, it gets really messy. So let's do it with an actual example. So, and we did this yesterday. So this is the Jacobian for Cartesian to polar. And the answer, the determinant of this is R. And the Jacobian for, what did I say? This is Cartesian to polar. This is polar to Cartesian. And the answer is 1 over R. So there you go. So we got the determinant of this one times the determinant of that one is R times 1 over R is 1. So they are inverses. Where'd they go? These guys are inverses of each other. So the Jacobian times its inverse is just equal to 1. So the determinant of a known mixed tensor is equal to the determinant of the transposed mixed tensor. So the determinant of any rank 2 mixed tensor is an absolute tensor, because this is true. Okay? That's it. I'll see you later.